Hello, everybody. Welcome back to Markov Processes. How is the homework going on our last week? Yeah, there's just two that maybe I want to bring up. If you're doing the optional 11th homework, you don't need to be looking at this at all, but it's also good review for the exam. So the final exam is not cumulative. I put in the announcements the actual date and time, and it's just another exam. So let me get my screen going. And yeah, just two things I wanted to mention about the current homework 11, which again is optional. So in problem 1, you want to show that the Gibbs sampler is a special case of the Metropolis-Hastings algorithm, and you're allowed to show it just for a two-dimensional chain. So remember, Metropolis-Hastings for a two-dimensional chain, if you have some target PDF, pi x1, x2, for Metropolis-Hastings, you want to pick out a candidate transition PDF, and we called that Q, and that's going to take us from a two-dimensional point, x1, x2, to a two-dimensional point, y1, y2, and we're going to propose a y1 and y2 from this Q, and we're going to accept a move from x1, x2 to a y1, y2 with probability alpha, x1, x2. So again, this is all Metropolis-Hastings, and then close that off, y1, y2, and that's going to be the minimum of 1 pi y1, y2, q, y1, y2, comma, x1, x2 over pi x1, x2, q, x1, x2, y1, y2. Close that, close that. So that's Metropolis-Hastings. And the Gibbs sampler says that we're drawing from something very specific. And so I would take that to be a candidate transition PDF, the recipe for the Gibbs sampler, and show that so for Gibbs, the probability of making a move from x1, x2, I say probability, but this is probably a continuous PDF, so it's not really probability, but like a probability, to the point y1, y2 is going to be, you need to draw y1 from the conditional distribution for x1 given the other x2, but this is supposed to be a PDF in the y's. So whenever I use pi of like x1 given x2, or pi of x2 given x1, those represent two different conditional PDFs. And if we ever plug in like a y, it still represents the conditional PDF for x1 given x2, but we've plugged in a y. So the y's do not have a different distribution. So in other words, this is all shorthand for pi of x1 given x2 evaluated at x1, and the given part evaluated at x2. And this guy up here is shorthand for the conditional PDF for x2 given x1 evaluated at these guys. And what I was just saying is this is shorthand for the conditional PDF for x1 given x2. Like there's no new distribution in here, but we're evaluating it at these 2 points. So to go back up here, which was unfinished, the quote unquote probability, because it's continuous, of choosing y1, y2 given x1, x2, you need to choose your y1 from the conditional PDF for x1 given x2, and then you need to choose your y2 from the conditional PDF for x2 given your already updated x1 that is equal to y1. So this is the transition probability for the 2D Gibbs. And my advice to you, if you're doing this homework, is to take this to be your Q. So make this your Q of x1, x2 to y1, y2 in the Metropolis-Hastings algorithm. And there was no accept or stay flat step for Gibbs, but show that your acceptance probability is always going to be 1. And that's why the Gibbs sampler is a special case of Metropolis Hastings. It's using a really specific candidate density. And then there's no accept move because everything is such that this thing over here is going to be greater than or equal to 1. So your acceptance probability is always 1. So there's no accept move. So let me know if that doesn't make sense. And then the other thing I wanted to say something about was problem 5. So it doesn't look like my normal Jackson network. It looks a lot nicer, and that's because I stole it from a book. And I didn't mean for R2 to have a value in the picture, but that's okay if you used it. This is a Jackson network with 2 servers, and I'd be happy to talk about how to get started, but no one's asked to go over any of them, so I will just move on. But what I did want to say is when you solve this Jackson network, the first thing you look at are flow balance equations. And that is when you let lambda I be the rate into and out of server I in equilibrium. So they should be balanced in equilibrium out of server I when the whole system is in equilibrium. So you want to first look at flow balance equations here. For example, well, okay, so we've got a server, and people are coming in at some external Poisson process with rate R1, and I didn't use lambda 1. I did edit part of the diagram. I didn't use lambda 1 because that could be confused with these lambdas, and people are coming in according to some external rate Poisson process with rate lambda 2, server 1, server 2, and then with probability 2/3, these people leave, and with probability 1/3, these people don't do that. They go to server 2. Yeah, so there's more, but again, no one asked me this. So you want to solve these flow balance equations and get a lambda 1 and a lambda 2. And then the stationary distribution for the number at server 1 and the number at server 2, this is a joint distribution. Looks like a couple of geometrics put together. The mu's are the 2 different service rates given as 3 and 5 in this problem. The lambdas are the solutions to the flow balance equations. And the allowable N1 and N2 is really anything that is a non-negative integer. So it asks for a minimum upper bound on R2 for which the system is stable. R2 was the input rate over here. I'm sorry, over here. R1 is the input rate over here. You're given all of the other numbers. So you need lambda 1 over mu 1 to be less than 1, or this geometric sum is going to blow up, and you need lambda 2 over mu 2 to be less than 1. So if you write out what these are in terms of your mu 1 given as 3, your mu 2 given as 5, your R1 given as 2, then you just want to choose R2 so that this system won't blow up, so that both of those are less than 1. And you want to choose, kind of just that sort of boundary case, because there's going to be many values for which it won't blow up. But what is the smallest upper bound on R2 for which both of these inequalities are satisfied? Okay, so let's talk about closed Jackson networks. There's not a whole lot new for us to do here, so it's not really a big deal. A closed Jackson network is one where you don't have external arrivals and you don't have departures from the system. You just have people moving around between servers. Network. This is also known as a Gordon-Newell network. And there is a version of Jackson's theorem for this that most people just call Jackson's theorem for closed networks, but really you should call it the Gordon-Newell theorem. So we've got M servers, just like we did with our generic Jackson network, and we have no external arrivals or departures. No one leaves the system, no one comes in. It's an awful lot of R's there. And I gave an example last time about kind of a made up example about like you having a factory and you having different machines at different stations. And maybe you're moving products in here and then they go here and maybe they're traveling around on pallets or something like that. And so you only have a fixed number of pallets in your system. That's my model. That's just an assumption. And sometimes they're piled up. Some of them are here, some of them are here, some of them are here. So that would be something that could be modeled with a closed Jackson network. And something I use this for is chemical reaction networks. And I'll give you an example of that rather than talk about that right now. So M servers, and you're going to have a total number of customers or pallets in that example. So capital N total customers stays constant in this system. Going to have an exponential rate mu I service time at station I or server I at station I. And so I don't know, here's an example. This could be server 1, server 2, server 3. We've got some capital N number of customers in the system, and maybe people can move back and forth. If they leave server 1, they can go to server 2 or server 3. If they leave server 2, they can go to server 1 or server 3, and maybe people from 3 can go back to 1. And I don't know, maybe that's it for this example. So you're going to have to be given some parameters here. The parameters are going to be the service rates at each server, and then the routing probabilities. And for this particular example, you'll notice there's only one arrow out of server 3. So people leaving server 3 definitely go to server 1. So from this picture, I can see that P31 is 1, but the other parameters need to be given. So like a P12, a P13, and actually those, because I don't have this in my picture, which I could, those have to sum to 1. So really only one of those has to be given. And a P23 and a P21. So these are positive parameters that need to be given, only some of which actually need to be given because, again, some of them have to add up to 1. So some of them get locked in. And so we want the stationary distribution for the number of customers at all 3 servers. So there's going to be someone in service and then people lined up. And we're going to have some number N1 up here, N2 and N3. And the Gordon-Newell theorem looks just like Jackson's theorem. We can show that this holds by using, you can use pi q equals r, but we actually got that out of the Kolmogorov differential equations, the Kolmogorov forward equation. You can get it out of the backward equation as well. And I think that proving this theorem, it's a little easier to go with the Kolmogorov equations, in my opinion, than the pi q equals 0. It's just hard to deal with a state space here, because if you were trying to make a generator matrix, then you would have states like 0, 0, 0, 0, 0, 1. You would have a lot of states to organize into a clumsy looking matrix. But it is stuff we've done. It's just tedious. And here's what we can show. So number 1, you solve the flow balance equations just like you do for a regular open Jackson network. Flow balance equations for these lambda 1, lambda 2 out through lambda m. In general, we have m servers. And then Gordon and Newell say that the stationary distribution for the number of customers at all of these servers, by the way, this looks like my continuous time notation. In my notation, this would be pi subscript n1, n2 out through nm. But that's a really hard subscript to write, with all those subscripts. So I'm using this more continuous state space looking notation. Anyway, it is proportional to the product as I goes from 1 to the number of servers m of lambda I over mu I to the ni. It looks a lot like it was before with the open Jackson network. And in fact, don't write this, but I can multiply by 1 minus lambda I over mu I in each term. And it looks a lot more like it did for the Jackson network. It's just that this does not involve the ni, and I'm already missing constants of proportionality. So that yellow term I put on the end just gets rolled into the constant of proportionality, because it's hard to find the constant because these are no longer independent looking things. You need, that's supposed to be white, come on, you need the sum of the n's to remain this constant capital N. And so finding the normalizing constant is usually not nice for large networks. So again, I could put the 1 minus stuff, but I can just roll that into the unknown constant. Okay, so let's try an example. I'm going to use the network I have above. Let me copy and paste this. And so I'm given some service rates, mu1, mu2, and mu3, and I'm given some routing probabilities. Like if I'm at 2, sometimes I go to 1, sometimes I go to 3, which means I'll have to be given the probability I go from maybe 2 to 1, and then the rest of the probability is 2 to 3. So in this example, the flow balance equations, we're going to let lambda I be the rate into or out of server I in equilibrium once this thing has settled down and has this balance of its flow. And so the rate in this particular picture example where the arrows represent all possible moves, the rate into server 1 appears to be the rate out of server 2 times this probability that we move from 2 to 1. So that's going to be lambda 2 times whatever is given as P21. And then I can also get to server 1 from server 3. So I'm going to take the rate out of server 3, which is lambda 3 times 1 in this case, because there's only one way to go from server 3. The rate into server 2 is going, so there's no external thing, and that's okay. Otherwise, it works exactly the same way. The rate into server 2 comes from this arrow, and that's it. That's the only way into server 2. And when I leave server 1, I can also go to server 3. So I have to take the proportion of the server 1 out rate that goes to server 2. So it's going to be P12. And then finally, how do I get into server 3? I get in this way and this way. So the rate into server 3 is the rate out of server 1 times the probability I go from 1 to 3 plus the rate out of server 2 times the probability we go from 2 to 3. Nothing has changed except right now we have a problem. You'll notice that there is a lambda I in every single term of every single equation. So if you come up with a solution, lambda 1, lambda 2, lambda 3, I'll take your solution and multiply everything by 8, and then I'll publish my own paper. There's an infinite number of solutions, not an infinite number of interesting solutions, not like an infinite number of linearly independent solutions, but for any lambda 1, lambda 2, lambda 3 you come up with, I can multiply by a constant. And because the constant will be everywhere across these equations, it will cancel. And so it won't matter what constant we use. So the solution is not unique. We have an infinite number of solutions, the solutions being lambda 1, lambda 2, lambda 3, and you can take any one of them. So why can you take any one of them? Because if you look at the form of the stationary distribution, if you solve for like a lambda 1, lambda 2, lambda 3 and use it, and I decide to use 8 times lambda 1, lambda 2, lambda 3, then my actual form of the stationary distribution is going to be that it's proportional to 8 lambda I over mu I to the ni. And if I pull out the 8s, then I'm going to end up with 8 to the n1 plus n2 plus n3 times whatever you had without the 8s. But this is a constant n. So this whole thing becomes part of the missing constant of proportionality. So it doesn't matter which of these solutions you grab for the flow balance equations. Yeah, so flow balance equations, infinite number of solutions, take any one. What I usually do is take something quote unquote convenient, and I might not know what that is until I finish my calculation, but I'm just going to take lambda 1 to be 1. So it's kind of arbitrary. But then from the second equation, you can see that lambda 2 is then p12, which is not arbitrary. P12 is a parameter of the model. And then from either of the first or second equation, let's look at the first equation. So if I take lambda 1 equals lambda 2 p21 plus lambda 3, and I plug in my two solutions here, p12, p21 plus lambda 3, then you can see that lambda 3 is 1 minus p12, p21. And I could have used the green equation. Everything is quote unquote balanced. So if I use the green, alternatively, if I use the green equation, I would have lambda 1, which is 1, times p13 plus lambda 2, which is p12, p23. And I can write p13 as 1 minus p12, because from station 1, I can either go to 2 or 3. So p12 and p13 have to add up to 1. And I can write the p23 as from 2, there's 2 arrows out of 2. I can go to 1 or I can go to 3. And I can write this as, I can write the probability of going from 2 to 3 as 1 minus the probability of going from 2 to 1. And if I multiply that out, I get 1 minus p12 plus p12 minus p12, p23, p21. So you can see that we do get the same thing as we got for lambda 3 up here. It's just like everything we've solved throughout the semester. There's always like one equation you can ignore because everything is all tied together. Okay, so the Gordon-Newell theorem, or Jackson's theorem for a closed network, says that the stationary distribution here is proportional to, let me go back up here. You take each lambda and you take each service rate. The service rates at server I is mu I, and you put this together. So we have 1 over mu 1 to the n1 times lambda 2, which was p12, p12 over mu 2 to the n2 times lambda 3 was 1 minus p12, p21 over the service rate at server 3, n3. And then we need n1 plus n2 plus n3 to be a given constant. So that's another parameter of the model, the total number of pallets in your warehouse. Yeah, so in general, it is hard to find these things. I sometimes use simulation to figure out what the sums are. And if you can't figure out what the constants are, you can estimate these probabilities by doing a Monte Carlo algorithm. So you can do, for example, Metropolis Hastings on this. One thing I can do is kind of simplify everything. If I write this last term as 1 minus P12, P21 over, let me back up. If you have an actual value of n, you can find the constant by brute force. You can sum up all these values and get a constant and then divide the whole thing by that constant. But I can also write n3 as n minus n1 minus n2. And then I can break that into 1 minus P12, P21 over mu3 to the n, and then that whole thing again to the minus n1 minus n2. And this is a constant. So I can drop it because I'm missing constants anyway. So why hang on to other constants? And because of these exponents, I can combine them with these, but I've got negatives here. So things will flip over, and I can write this as pi n1, n2, and then n3 is just locked in, is n minus n1 minus n2. This is going to be mu 3 over mu1, 1 minus p12, p21, not equal, sorry, proportional to the n1, and mu3 p12 over mu2, 1 minus p12, p21 to the n2. No one can read that. Let me pull this out. And I do have a restriction on N1 and N2. So the state space here is going to be N1 could be 0 customers, 1 customer, up to all N customers, all capital N customers could be at station 1. N2 is not just like N minus N1. This could be anywhere from 0, 1, up to N minus however many are at N1. And then N3 is going to be forced to be equal to N minus N1 minus N2. So the sort of state space in N1 and N2 looks like 0, 1, 2, up to N, and then 0, 1, 2, up to N minus 1. So 0, 1, and you get kind of a triangular thing that eventually, it's a discrete state space, but it's a triangle. So this is the point where N1 is 0 and N2 is the full N people in the system. And I might do Metropolis Hastings on that. And I might actually, I don't know, I might actually try drawing like as a candidate, using an independent candidate and drawing uniformly from this weird triangle. What if you, just for fun, what if you wanted to draw uniformly from this set of points? So let me fix an N, like 0, 1, 2, 3, and then 0, 1, 2, 0, 1, and 3, 0. So like if I wanted to draw independently from this group of points, I have 4, 3, 2, 1. So I've got 10 points, and I want to draw them all with probability 1/10. I want to have probability 1/10 of getting any one of these. And so you can't draw the N1 and N2 coordinates independently because you can't, because you want to end up in here 4/10 of the time, and you want to end up in here 3/10 of the time, and you want to end up in here 2/10 of the time, and you want to end up here 1/10 of the time. So you would have to do something like interval chopping to grab a uniform and say, go up to 4/10 and then up to 7/10, which is a width of 3/10, and then up to 9/10, which is a width of 2/10, and then the remaining 1/10. So you could draw a uniform, and if it falls in here, then you want to draw from this row dots. And then once you're in there, you can uniformly draw from the 4 dots in there. But I've totally digressed. I don't want to Metropolis Hastings this, but you can do it with a discrete state space. Let me look at, so I told you at the very beginning of class that I wanted to show you some of my current research at the end, and it has to do with these queuing models and chemical reaction networks. You do not need to know anything specifically about chemical reaction networks for the final, but as you'll see on the review problems for the final, I can describe one for you and have you solve it as a Jackson network, but it would have to be completely described for you, so you don't need to know any extra information about them. But usually they are depicted by, this is the sort of simplest one I can think of, where you have a container filled with some number of A molecules and some number of B molecules. And chemists put rates on these arrows, or rate K1 and a rate K2. And what that means is that you have some number of A molecules, and some number of B molecules, and you have a total of some number, so total of maybe N molecules. And each A molecule, so you have them stirred into a container, each A molecule is racing to turn into a B molecule. And they're exponential races. That is the general assumption behind a basic chemical reaction network. So if there are, let me just say, each A molecule will transform into a B molecule after an exponential amount of time with some rate K1. That's what the chemists use, Ks instead of lambdas. Amount of time with rate K1, and then each B molecule, blah, 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 exponential amount of time with rate K2. So this is something we've seen before in this very simple chemical reaction network. This is like the urn model, where we had like balls jumping back and forth between two urns, which is known as the Ehrenfest urn model, which I think I mentioned a few times, but I always specifically did not write that when I had a homework problem based on this, because I didn't want you to look up the Ehrenfest urn model. And we know how to solve for the stationary distribution of the number of A molecules and the number of B molecules, because this is just a simple birth and death process. Because if you know the number of A molecules, you definitely know the number of B molecules. So one way to do this is a birth and death process. And we can talk about maybe like pi sub A being the probability there are A molecules of A in the system. And if you really wanted to talk about a joint PDF for like, call this I don't know, we have many notations here. The B is always N minus A. So you can follow just the A molecules. You can treat it as a birth and death process. If there's currently 0 A molecules, then all capital N of those molecules are over on the B side, and there will be capital N of them, each racing to turn into an A molecule after an exponential amount of time with rate K2. So the overall rate is N times K2, because if there's 0 over here, then there's all N over here, and N of them are racing, and that's the time of the next event. And so I'm thinking of it as a birth and death process where I'm tracking the amount of A. And this looks like everything else we've done, so let me just write another one out. So if there's currently one A molecule, then there's N minus one B molecules. And after an exponential amount of time with rate N minus one times K2, I had these arrows, right? I had K1 going from A to B and K2 going the other way. Then we will go from one A molecule to two A molecules. Dot, dot, dot. If there are if all N of the molecules are on the A side, then there is no motion to the A side. So the rate there is zero. And mu zero, if there are zero molecules of A, then molecules of A are not dying or departing. There aren't any. If there is one molecule of A, it will move to a molecule of B after an exponential amount of time with some rate K1. If there's two, they are racing and we get 2 K1. If there are all N, they are still racing and K1. And you can use the old birth and death process. And you will end up with, let me just do this. You will end up with capital N, choose little n being this number here. We're just following A molecules times K2 over K1 to the A times pi 0. I can think of at least 4 different ways to find the stationary probability. Everyone looks completely different. But if you can find the normalizing constants, then you'll see that they are exactly the same. And this, I need to find pi 0. So I need to set 1 equal to the sum as n goes from 0 to capital N of the pi n's, and that they all have a pi 0 is going to be the sum as n goes from 0 to capital N, and choose n, K2 over K1 to the, this should not be an A. Either this needs to be an A or this needs to be an N. Sorry about that. This is an N. The N, and this is binomial looking, especially if I put a 1 to the N minus N, I will get pi 0, K2 over K1 plus 1 to the nth power, which is pi 0, K1 plus K2 over K1 to the nth power, which means that pi 0 is K1 over K1 plus K2 to the N. And if you go back and plug it in here, then our pi N is N, choose N, K2 over K1 to the N, K1 over K1 plus K2 to the N. Little n could be 0 or 1 or 2 up to N. And it looks kind of binomial, especially if you break this up into, you can actually rewrite this as N, choose N, K2 over K1 plus K2 to the N times K1 over K1 plus K2 to the N minus N. Yeah, so this minus N on the K1 comes from this, and yeah, that's all valid. So it looks like a binomial. I thought it would be fun to come at this from several different ways, but I guess it's not all that fun. So I treated this as a birth and death process, but you could treat this as a closed Jackson network. And so I'm currently working on, I have a paper coming out soon this summer, which is relating all of the results from chemical reaction network theory to queuing theory and vice versa, because it's a case where people in two camps don't know what is known by the other camp. And it's not completely equivalent, because if you sometimes have these chemical reactions where a molecule of A can turn into 2 molecules of B, and 2 molecules of B can combine to form a molecule of A. And this would be like 2 customers somehow leaving at the same time, and one goes away and one goes to the other station. So it's not as straightforward as it looks, but yeah, I'm trying to unify the theory right now of chemical reaction networks and Jackson networks. How exciting is that? Okay, so that is the end of the course. Final thing is to talk a little bit about perfect simulation. This is totally for fun. You're obviously not going to do, I don't know, obviously, but you're not going to do simulations on the final, but you may have to answer questions about the Gibbs algorithm and the Metropolis Hastings algorithm, and I will put those in the review so you could see what kinds of things you could be asked. I always put those kind of simulation questions in the review and never really ask them, but this time there's a good chance of that because there's just not that much new material since the last exam. So, but I will stick to my normal, if it's not on the review, it's not on the final. That'll be coming out this evening. I want to tell you about perfect simulation. This is what I do. This is a really cool idea that was first proposed by two guys named Propp and Wilson, James Propp and David Wilson. They were both at MIT at the time. Wilson was Propp's grad student. So this is MC without any convergence error. And if you want to sign off, sign off. I won't be insulted. This is just for fun. You won't not be tested on this. Yeah, you get to see infinity, which is what anyone who sits next to me on a plane finds out when they ask me what I do for a living. I start drawing on napkins. I feel like I see infinity, and they really regret asking. So here is a toy example. This is the example that Propp and Wilson came up with, and what I spent many years of my life doing was trying to make this so that it will work for real problems. So let's go to a discrete state space, like 0, 1, and 2, with a given probability transition matrix. So like way back to the beginning of the course. And I want to simulate values from the distribution pi, which is made up of a pi 0, pi 1, and pi 2, the stationary distribution for this chain. You would never do this by simulation because it's a small system of equations to solve for pi 0, pi 1, and pi 2. And if you can solve for them, and maybe you get pi 0 is 5/12 and pi 1 is 2/12, pi 2 is the remaining 5/12, well, then you can simulate values by interval chopping. You know, once you know the pi's, you can simulate and produce a value 0 with the right probability and 1 with the right probability, and so on. So there's no point to use MC on this problem, but it's just our sort of motivating example. Okay, so what you would do is if you didn't know how to find the stationary distribution, you would make up a state space and you would have time and you would start at an arbitrary point. And then you would grab a uniform like associated with time step 1. So I'll call it U1. And if you happen to be at state 1, then you would look at the one row of the matrix. This is not perfect simulation. This is regular simulation. You would look at the one row of the matrix and the 3 different probabilities given there, and you would compare the uniform and you would do that interval chopping and you would figure out whether you go to state 0 or 1 or 2 and you would move. And then in the case that you move to state 2, you would now focus on the 2 row of the matrix and you would grab another uniform associated with the next time step. And you would look at the 2 row of the matrix and compare your uniform with these 3 and try to figure out where you go. Like maybe you would stay flat. And you would go for a long time. We've seen many examples of a long time not being that long, but it could be. I mean, there's certainly Monte Carlo examples of a long time actually being a long time. And so you go for a long time and you grab output and you start building up your distribution. And it is not perfect because you have sort of chosen this point to go out to. So here's how you do this perfectly. You go backwards in time. So here is the perfect simulation of the same thing. I've got a state space, 0, 1, and 2. I have a probability transition matrix filled with probabilities. And you look in backwards time. So this is time. This is time 0, time -1, time -2, etc. And then this is your state space. So 0 or 1 or 2. And you start at time -1 and you look at every single point in the state space. Now that is ridiculous for a state space with more values, or a continuous state space, or a continuous state space on high dimensions. And as I was saying, that's what keeps me in business. I actually make this work for interesting Markov chains. You grab yourself a uniform associated with this time step, -1, and you look at the uniform and you look at every single point in the state space. So you look at when you're at 0 and you compare your uniform to the things in row 0 and you go forward somewhere. Using that same uniform, you look at the one row of the matrix and you simulate forward using that uniform. And the same thing starting from 2. So basically I'm simulating forward for one step from every single point in the state space. That seems like that's going to be intense. It's not necessarily going to be intense. So then you go back to time -2 and you look at every point in the state space and you grab yourself an independent uniform 0, 1, and you look at the 3 rows of the matrix and you go forward, and like maybe this goes here and maybe this goes here and maybe this stays flat or something like that. Then you go back to another time step. Oh, you'll notice I appended onto the previous paths. That is crucial here. This appending onto the previous paths. Let me go back one more step, and maybe from here I go to here, and maybe here I go to here, and maybe here I go to here, something like that. And something has not happened. I got to go back another step. Okay, so maybe from here I go to here, and here I go to here, and here, oh, come on. I go to here. Okay, so now going forward from these points, I believe I have done this. Every path forward to time 0 ends at the same place. This is what you're looking for. You go back until this happens. This is known as a backward coupling time. It is a random point in time, and I claim that this is the tail end of a path that has run for an infinitely long time. It is, really. You could start back at -infinity and simulate a single path. And then at this particular time here, -4, it has to pick one of these. And so it has to funnel through to this point at time 0. So this is the end of a sample path that has run for an infinitely long time. So you're going to output in your algorithm 0. And there's no error because it's run forever. And it was crucial that we appended onto the previous paths, because otherwise there's nothing backward about it. So if you were to start at time -1 and just go forward and say, those paths didn't meet, let me erase them, and now I'll start from time -2 and go forward with completely independent uniforms, there's nothing backwards about it. You're just trying something for one step, then you're trying it for 2 steps, and you're trying it for 3 steps. By the way, you don't have to store all of these. You can recreate every path you need by storing the uniforms. So you really only need to store these pieces of information as you go. But if you don't append onto the previous paths, which is equivalent to reusing the previous uniforms, right? Because if I erase these and lose them, and I go forward from time -2 to -1, all I need is to have that uniform to tell me where these paths will go. So I don't need to actually, like store all those. Then I claim that if you don't store them and append, that there's nothing backwards about it. So why not do this? Why not start at time 0 and look at every point in the state space. And I know what you're thinking, you have an infinite state space or something like that. If you can go until all of these kind of meet, then where are you going to stop? Are you going to stop the first place they meet? Because I can make up chains for you that can only meet at the top or bottom of the space. I can just have random walkie type chains where they all go up or down. And the only way they meet is if they all pile up on the top or all pile up on the bottom. The real problem is that stationarity holds at fixed time points. So we have our stationary equation for an n-step transition probability, but not necessarily if this is random. We then have trouble, and this is random. What you can do is start at time 0 and fix a very large time. And if you started at every point in the state space and they all came together at some point and you kept going to a fixed time, then this would be a draw from the stationary distribution, because if you started back at minus infinity, any path would have to pick up one of these at time 0, and this would be the tail end of a path that has run for time minus infinity plus 1. But the very first time, once you set this time, the very first time, your paths do not all come together before this point, and you have to move this output. This has now become a random point in time. Equivalently, the very first time all your paths do not come together by this time, if you decide to just throw out that run of the simulation, you are actually biasing the draws. So the key to perfect simulation or backward coupling is to always have a fixed time point, which is time 0 in this setting. Yeah, this is super, super cool. And it could be super hard to apply for real problems. In the remaining time, I would like to show you one of my algorithms, which is based off of the Metropolis-Hastings algorithm with an independent candidate Q. And it's known as the perfect IMH algorithm. IMH standing for independent Metropolis-Hastings, and independent meaning that the Q, the transition, the candidate density is independent of where you are. Check this out. And so your target is some pi of x, which is likely on a continuous state space. So how the heck are you going to start from all places? You can't on a continuous state space. And if it's unbounded, even worse. And you take an independent candidate for Metropolis-Hastings. So a QXY equaling some Q of Y, right? So if you're currently at X, you would choose Y from some distribution that doesn't depend on X, and then you accept the move or not accept the move. I'm going to make this perfect, which will give you one sense of how you might deal with an infinite state space. So this sounds awful, but you don't actually do this. You reorder the state space. In practice, you don't do this because I wouldn't want to do this. So you define a state X to be less than or equal to, I should probably use some sort of partial ordering notation. I'm just going to put in quotes. I define it to be less than or equal to Y if the pi of X over Q of X is greater than or equal to pi of Y over Q of Y. And this is a true greater than or equal to in the sense of the ordering of real numbers. This means that, note, you always accept moves down, where down has been redefined. Because if you are at X and you propose a Y and the Y is smaller than the pi of X over Q of X has to be actually smaller than the pi of Y over Q of Y. And that means that if you multiply this to, flip it to the other side, that pi of y, q of x over pi of x, q of y is greater than or equal to 1. And that's the acceptance probability. If you propose a y, you're going to move there with minimum of 1 and this thing, but it's always greater than or equal to 1. So you always accept moves, quote unquote, downwards, but downwards has to be defined. So if I were to draw the picture, if I have a state space here that is even infinite and continuous, this is not continuous looking. It looks like a bunch of points, but imagine this is a whole continuum of points. So at time 0, I propose a value from Q. And in this reordering of the state space, anything quote unquote above, so this is reordered, will accept a move down. Anything, no matter how high it is, I can keep going up infinitely high. This looks like it's above, above, above. And then we could show that that the ones below may or may not accept that move, depending on the uniform you would draw to determine acceptance. But you could show that if any one of them accepts the move based on a uniform, that the ones above will also accept the move, and potentially everything below that will stay flat. So you will get everything coupled and coming together. If the lowest point accepts the move, then everything will accept the move. So this is a low point, and it is the x that small points have large pi over q ratios. It's the x that maximizes pi of x over q of x. So you have a target distribution, you choose your favorite independent candidate distribution, you form this ratio. If you can maximize this, you are good to go. If not, you have to choose a different Q, but you don't need to think about the whole state space. You just have to go like this. I have identified a point low that maximizes the pi over q ratio. You imagine it sitting here, and there's some weird ordering of points. And you propose a Q, and you say, do I accept this move or do I stay flat? If I stay flat, you go back. You save that uniform. And you say, I'm going to propose another Q. Do I accept this or do I stay flat? And the first time you accept the Q, everything else is guaranteed to accept it. So you have a continuum, infinite number of states that will accept that point. And in order to have the fixed number of time points, you always have to follow through to time 0. So now every path is here, and you can either accept this Q or stay flat. And if you stay flat, you can either accept this Q or stay flat. Well, in this picture, I would definitely accept because it's going down. But this is the perfect IMH algorithm that forces the whole continuum of paths together in one shot. And you only need to identify the low point and figure out how far you have to go back before it accepts a point. And in practice, you're like, here is some low point that I'll call L or something like that. Does not accept, does not accept. Oh, does accept. Now you take your other cues and follow through. And this is the perfect draw, because everything at this time would have to accept that point. So you get this backward coupling of points of paths. Perfect IMH algorithm. Yeah, so other fun things is, you know what you can do if you are running a Markov chain that has some actual transition density, like a PXY on a continuous state space, you can start flipping strange coins with strange probabilities at each time step. And if you get heads on your strange coins, you can artificially smash all the paths together. And if you get tails, you have to draw from something very strange that will make the overall path run according to the original transition probabilities. You have to compensate for the fact that you threw in this coin in a way that doesn't disturb the transition probabilities, but you can compensate in a way that can smash paths together. So you can get this so-called coupling, and it's really darn cool. So we have 2 minutes, but there's nothing I could possibly explain in 2 minutes. So now you have 1 minute. Go enjoy your 1 minute. I will get review problems out tonight, and we will review on Wednesday. And as usual, I have some time to stick around and talk about the homework if anyone's doing the optional homework. But I will see you next time on Markov processes.
Hello, my baby. Hello, my honey. Hello, my ragtime gal. Send me a kiss by wire. Baby, my heart's on fire. If you refuse me, honey, you lose me. Then you'll be left alone. Oh, baby, telephone and tell me I'm your own.